All right, in our second video for 1.2, we're going to talk about a few more characteristics, starting with boundedness. A function that is bounded above means that the function has either a maximum or a horizontal asymptote above it, and it has like a ceiling then. So you could have something like a upside down parabola because that has a maximum, or maybe I'll put one here with a horizontal asymptote where the function is below it. Those would be bounded above. Bounded below would mean that the function has kind of like a floor instead of a ceiling, and it would have a minimum or a horizontal asymptote. So maybe a absolute value function that's opening up because that would have a minimum point, or a function that has an horizontal asymptote where the function is above that horizontal asymptote. That would be bounded below. If a function is both bounded above and below, we say that it is bounded. So if it's bounded both ways, let me just say it's bounded. So that could be something like the sine or cosine function, because that has minimums and maximums that it just keeps bouncing back and forth between. It could be something that has two horizontal asymptotes. There's a function that we'll deal with called the logistic growth function that has two horizontal asymptotes. Looks kind of like this. That would be bounded. And another type that we could have is just a function. I'll just draw a polynomial function, but its domain has been restricted. So it has endpoints. So maybe it looks something like that. Actually, I'm going to go just, I did it again. I want to make one endpoint just higher or lower than the other. Okay, so that function is some sort of polynomial function, but it has endpoints. So it has both a minimum right here and a maximum value right there. So it is bounded. So let's talk a little bit more about these minimums and maximums. We lump those together with the word extrema. When we're talking about extrema, there are two types, relative and global, or also known as local or absolute. We use local and relative kind of interchangeably, and we use absolute and global interchangeably. Local or relative are when you have y values that are bigger or smaller than just others that are close by. So, in other words, they'll be either a minimum or maximum just within an area. Absolute and global are the overall maximum or minimum of a graph. One other little caveat is that endpoints cannot be local or relative extrema, but they can be absolute extrema, just by definition. So if you look at this picture here, we got some x values down on the axis there. I don't know why they're not in order, but the x values are the letters down on the axis. Their corresponding y values are what we're going to talk about as being the maximums and minimums. Maximums and minimums extrema are always y values. So if we look here for what the highest point on the graph there, that would be E, or at E, so that would be the y value f of E. F of E is the global or absolute maximum. We could also say that it is a relative or local as well. Let's find the absolute minimum here. That looks like it would be happening at A, so the y value f of A is going to be the global or absolute minimum. We can't call that guy a relative or local because it is an endpoint. F of C and f of D are both just locals. F of C is a local, or also known as a relative max, and f of D is a local or relative min. And you don't have to use both words all the time. I just use both so you see them both. You can either use local or relative. You can either use global or absolute. You're just going to see them both. The only one that we haven't talked about yet is f of b. F of b, since it's an endpoint, can't be a local or relative minimum. It would be if this continued on like this. But since it doesn't, f of b is not an extrema point. It's not any sort of minimum or maximum. Okay, the next thing we're going to talk about is symmetry. And we use the words even and odd to describe symmetry over either the y-axis or origin. Maybe you want to pause the video and get some of this stuff down, or just write as you go. Just understand that the words even and odd, we're not saying that it's an even polynomial function like x squared or x to the fourth necessarily, or an odd polynomial function. It's not just talking about the degree, although there is some interchangeability there. We are speaking, oh, actually, I got to fix this one. This got shifted. We are speaking strictly of the type of symmetry being even or odd. To have even symmetry means that you have a graph that is symmetric over the y-axis. So that graph that's shown there in pink has even symmetry. If the point A comma B is on that graph, then we also know that the point negative A comma B would be on that graph. Numerically, I just throw out an example here. If I told you that f of 3 equaled 7 with an even function, we would know that f of negative 3 would also equal 7. We're going to prove that a function is even or odd in its symmetry algebraically by finding f of negative x, and we'll do an example of that below. But to prove a function is even algebraically, we're going to put negative x in to the function and verify that it equals the original function. Odd functions are symmetric over the origin. What that means is that you could reflect them uh, both horizontally and vertically, and they would become the same graph. Or you could turn the graph upside down and it would look the same. That's what it means to be symmetric over the origin. They look the same right side up as they do upside down. If the point A comma B was on the graph, then the point negative A negative B would be on the graph. And if I told you, just as an example, that f of 3 equals 7, you know that f of negative 3 would equal negative 7. To prove algebraically that a function is odd symmetrically, again, we're going to put negative x into the graph, but this time we're looking for it to equal the opposite of f of x. The third type of symmetry that we have is symmetry over the x-axis, but the problem with that is that's not a function. That would fail the vertical line test. These are not functions, but they still have symmetry. We know that if the point AB was on the graph, that the point negative AB would be on the graph as well. To prove this algebraically, you can't, because it's not a function. All right, let's talk about the whole proof algebraically thing a little bit deeper here. To prove a function is either even, odd, or neither, the first thing we're going to do is find f of negative x. In other words, we're going to put negative x into the function. If it is the same as the original function, or in other words, if f of negative x equals f of x, it is an even function. However, if putting negative x into the function gives us the opposite of the original function, then it is an odd function. And then if neither of those things are true, we'll say that it's neither. Got a few examples down here. We're going to start in example A. Well, we're going to start the same way in all these examples. We're going to put negative x into the function. So I'm going to start by saying, if that's f of x, then f of negative x would be 5, and then I'm just going to put negative x everywhere I see an x. And then I'm going to simplify. Negative x squared becomes x squared, so this would become 5x squared plus 5. And hopefully you notice right away that that is the same as the original function. Since f of negative x equals f of x, we can say that that's true, therefore this is an even function. We just proved that algebraically. We could use graphing to show that it is also even, but we're asked to do it algebraically, so we have to put negative x in. In the next one, we have, or we're again going to start by putting negative x in. Now I'm going to simplify. This is going to simplify to 3x squared minus 8x plus 12. So that's not the original function because that term switched. And it's not the opposite of the original function. The opposite of the original function would have all the terms switch sides in a polynomial like that. So putting negative x in did not give us the original function. I don't know what's going on there. It did not give us the opposite of the original function. So this is neither. Our third example here, we're going to start by, again, putting negative x in for x. And then we'll simplify. That's going to become negative 5x cubed because a negative cubed becomes negative. Negative 6 times negative x is positive 6x. So that's not the original function, so it's not even. But it is the opposite of the original function because both signs changed. F of negative x equals the opposite of f of x. Therefore, this is an odd function. We just proved it algebraically. All right, we're going to wrap up this section talking about limit notation. Some of this is really not necessary because we started teaching limit notation in Algebra 2. So some of this was trying to connect it to a different way that we used to do in Algebra 2, which is like that. But you've seen limit notation already in Algebra 2. There's an example of limit notation. What that is saying is as we go to the right on the graph, because it says, to the left. As we go to the left on the graph, because x is approaching negative infinity, the graph itself is going up because it approaches positive infinity. Take a look at this first example here. End behavior is only dealing with what it's doing as it gets further away from 0. So as we approach negative infinity, it's going up. As we approach positive infinity, it's also going up. I don't know why I put a negative there, I'm sorry. But we're going to write that using limit notation. So for limit notation, you start with the word L, or the abbreviation for limit, LIM. And then underneath it, you're going to talk about which direction you're looking. We're looking we're looking for the limit as x approaches negative infinity first. And we're going to do this top one. And then I'm just going to put what I'm looking at. I'm looking at a function f of x. I don't know what the function is, so I'm just going to use f of x. And I know that as we go to the left, negative infinity, it's going up. But since I know it's going up in the other direction, what I'm going to do is just put this all in one neat little package here and say that the limit as we go to the left equals the limit as we go to the right. That's an infinitesimal, which in turn equals the same thing, which is positive infinity. You can't put a positive negative infinity right there and do this with one limit. That is not allowed, if you were wondering. All right, the next one, same idea. You are only looking as we go to the left and as we go to the right. This means nothing when it comes to end behavior. Okay, now there's some sort of vertical asymptote there, which we can describe using limits, but we're just asked to describe end behavior here. So I'm going to ignore all that. I'm not saying you have to cross it out, but just ignore it. And I can tell that as we go to the left, the function is going down, and as we go to the right, the function is going up.
Good afternoon, ladies and gentlemen that are riding the bus. Please be aware there is no Route 18 you will once again ride on Route 8 or 14 based on what you've done the last couple of times. I'm so sorry for the late notice on this, but once again, students riding bus route 18, please note that you will be riding bus route 8 or bus route 14 as we've done earlier this week. Natalie Stitchen, we do have a quick trip gift card here for you. Thanks for your donation to the hoodie drive. And Bree Howard, please report to our main office at this time. Daily Schmaltz, if you're here, stopping guidance. Thanks so much. Wishing everybody a wonderful weekend. Get up and enjoy the weather. Good luck to all the owls competing this weekend. Take care, everyone.
All right. Hopefully they don't miss their bus. Okay. There is no pause button on this thing. Otherwise, I would just pause when that sort of thing happened, but there isn't. Okay, so as we look at this one, the only difference here is that this isn't approaching positive or negative infinity as we go to the left. As x approaches negative infinity, this thing is actually getting closer and closer to the value right here, which is -3. There must be a horizontal asymptote there. You could even draw it in there if you wanted to. Horizontal asymptote at -3. So as we go left, this thing is approaching -3. As we go right, it's approaching positive infinity. So if your limit, which I'm about to write right here, is approaching a number, that is a telltale sign that you have a horizontal asymptote there. So as we approach negative infinity, as we go left, this function is approaching -3. As we approach positive infinity, this function is approaching positive infinity. All right, so if you were wondering, well, how do we describe stuff like that in the middle, that vertical asymptote sort of thing going on, that's what the next section is about. When we are describing what happens at a particular x value, so not end behavior, but at a value of x, then what we want to do is approach it using a one-sided limit from both the left and from the right. So this notation right here, the only thing that you can tell has changed, well, now we don't have infinity, we have a number, which I'm just representing with a, and then we have this little plus sign right there. That means that we're going to be approaching from the right. As we approach a from the right here, I'd be going down to negative infinity. So this is going to be negative infinity. That is the right-sided limit that approaches a. The left-sided limit, as we approach a from the left, that thing goes up to positive infinity. So that would put a little negative superscript on that letter A, or on that number, and that one is approaching positive infinity in that example. Those are each called one-sided limits because you're just looking at it either from the left or from the right. Now, if you notice over here, I have a normal limit, which is actually called a two-sided limit. It doesn't say minus or plus, so that just means what does this function approach as it approaches a? Well, if the two one-sided limits aren't the same thing, there's no way that this limit is approaching anything. This limit does not exist. And I'm just going to write because the one-sided limits that we just did are not equal. If they were equal, then that two-sided limit would be the same thing as well. So if we were to write a limit for this one, both the left and the right, if I were approaching 0 from the left and from the right, they'd both be approaching positive infinity. So I could say that as we approach 0, it approaches positive infinity. All right, so we're going to break that down a little bit with some functions down here. We got 1 over x minus 3. I'm going to do a quick sketch of that graph. That has a vertical asymptote at 3 because I know x cannot equal 3. So I got a vertical asymptote right there. And then it is basically going to be the function 1 over x. I'm going to sketch it in right there. So it's going to have a horizontal asymptote at the x-axis, so the end behavior. Does it ask us to talk about end behavior? Nope, it just says what happens at x equals 3. describe the discontinuity using limits. So there's a vertical asymptote at 3. It's asking us what's happening at 3. There's a vertical asymptote at x equals 3. And I'm going to describe that with limits. I know that as I approach 3 from the left, which would be from this side here, as I approach 3 from the left, it's going down. I could either put 1 over x minus 3 here, or I could just write f of x, which I'm going to do. That approaches negative infinity. The limit as x approaches 3 from the right, that's going up as we approach it from the right, so positive infinity. So the two-sided limit does not exist. All right, looks like we're going on to example B down here. I do have a little reminder here. Vertical asymptote at x equals 3. I know we talked about vertical asymptotes already, but I'm just going to remind you that this is an infinite, non-removable discontinuity. Remember, vertical asymptotes are non-removable. Anytime we can get some terms in there, it's a good idea. All right, in B, we can actually factor both the numerator and denominator. Actually, the numerator. And since I have a common factor of x minus 3, I'm going to remove it. Don't lose it, though. This is just going to become the line y equals x plus 3, except it's going to have a hole at 3 comma something. Instead of writing at x equals 3, a hole is a missing point. So I'm going to do it with a coordinate. To find the y value, you got to put the x value back into the line where the hole is. So if I put 3 back into that, I'm going to get 6. So now I'm going to just do a quick sketch of the line y equals x plus 3. So it's going to have a y-intercept at 3. It's got a slope of 1. But I know at 3, comma 6, so not really to scale, but close enough, it's going to have a hole. So let's get some limits going here. And then before I go, I'm going to write that this is a non-removable discontinuity. Just kidding. It's removable, right? We removed it right there. All right, so let's use some limits here. Let's approach 3 from the left. Let's approach 3 from the left. Ooh, this is g of x. Switched it up here. Look at that. And we're also going to approach it from the right. Just getting kind of ready here. And then we'll do the two-side limit, see what that is. All right. As we approach 3 from the left, it is getting closer and closer and closer to that y value of 6. As we approach from the right, it is getting closer and closer to that same y value of 6. Since those two numbers are the same, that means that the two-sided limit is also the same thing. The limit as we approach 3 of that function is 6. Here's one more thing I'm going to add into this, though. If I ask you to find f of 3, there's a hole there. It doesn't exist. That idea right there proves that there is a hole there, that there is a removable discontinuity. All right, last one. So we've got a piecewise function that we're going to graph here. I've got a line up until x is 3. So I know that x equaling 3 is kind of important. I'm just going to put a 3 right there. I'm going to graph the line 2x minus 1 until that point. So 2x minus 1, the y-intercept of -1, and the slope of 2. We'll get a couple points on here. And what I want to make sure I do, though, is once I get to the value of 3, which I know is going to happen at 5, because I can put 3 in there. If I put 3 in there, I get 5. But I could just continue my line, too. But I'm going to put an open circle, because it says only if x is less than 3 do I want to be that line. So there's that line right there. And then I have the graph of negative x squared plus 2x plus 6. All right, little review of graphing a quadratic here. I'm going to find my vertex by doing negative b over 2a. Negative b over 2a. So I'd have negative 2 over 2 times negative 1, which is also negative 2. So I have an x value of my vertex at 1. Now if I put 1 back in, I get negative 1 plus 2 plus 6, or 7. So now that I have a vertex at 1 comma 7. 1 comma 7, but that's not actually a point that I want to graph, because that's a value that is greater than or equal to 3. But what I'm going to do is I'm going to erase it in a second here. I'm going to put it there to get myself started. 1 comma 7 is right there. Just put a little dot there that I'm going to erase later. Then I know that because this has a negative 1 as an a value, that the table that I want to use from 1 comma 7 is 0, 0, 1, negative 1, 2, negative 4, 3, negative 9 from that vertex. So 1, negative 1 would be there. 2, negative 4. 1, 2, 3, 4 would be right there. That one is going to be the first point that I can actually see. And then 3, negative 9 would be one more over. I went down 4, so 1, 2, 3, 4, 5 more would be right there. Let's go another one. 4 comma negative 16. Go one more over. I went down 9. I need to go another 7. 1, 2, 3, 4, 5, 6, 7. That's a good looking parabola right there. All right, so there is the parabola that I can see. And if I continued it on, it would go through those points there and obviously continue on, but I don't want that part. There is our piecewise function right there. All right, now they want us to describe what is happening at 3 in this function. So I'm going to do the limit as we approach 3. I'm going to come from the left first. As we come from the left, this limit is approaching, or the y values are approaching the value of 5. As I come from the right, I'm going to make that the same color as my graph. As we approach 3 from the right, those values are approaching not 5 this time, but that value right there of 3. Oh, you know what? I think I messed up. This function is called h. Glad I caught that. I want to change that to h of x right there. Details. It's Friday. You hear people leaving school, not paying attention. All right. So this is approaching 3. And since those two values are not the same, I know that the limit as x approaches 3, the two-sided limit does not exist. Okay, and this is also another way that you can tell there's a jump there. It is approaching 2 different values. This is a jump, which is non-removable. All right. I think that's really all we need for that one. We got our limits. We described what it was a jump. I'm going to get rid of that green arrow right there. Didn't like how that looked. All right. So that's the idea of using limits to describe what's happening as you approach an x value. We use limits for different things. This is describing approaching a value. These limits were being used to describe end behavior. So make sure you're kind of separating the difference. End behavior, you should be approaching positive, negative infinity with your x value. If you're approaching an actual x value, you're going to have a number with either from the right or from the left signified.